Good afternoon, everyone, and thanks to the organizer for this kind invitation. As you probably guessed from the title and the abstract of this talk, this presentation is intended to give some background about semantic web technologies applied in the cultural heritage domain, even for those that are approaching with these topics for the first time. This talk is split into four main section, as you can see in the slide. In the first one, I'm going to give you some exploration about how these two fields, semantic web and cultural heritage, intersect, and how semantic web can address some challenges in the representation of cultural data. In the second part, we move from ontologies to knowledge graph, and in particular, we'll focus on the theoretical foundation of the ontology under the computer science point of view, and we'll explore how it's possible to develop, to design an ontology, and how it's used to structure and connect information. The third section focus on two ongoing projects I'm currently working on. The first one is an ontology called Bistiris, while the second one is a knowledge graph developed within a project named Women Writing Around the Camera. Finally, we'll conclude with some final remarks. So let's start with this first part. I'm quite sure that many of you already are familiar with the concept of semantic web, but I think that it's important to make sure we are on the same page. Over 20 years ago, Tim Berners-Lee described the semantic web as a web of data that can be processed automatically by machines. Unlike the traditional web, which mainly focuses on web pages, documents, the semantic web focuses on connecting data. This vision introduced a paradigm shift with a few key differences between these two web, the traditional one and the semantic web. First, the main key difference relies when it comes to searches. The traditional web uses basic keyword searches, which can lead to broad or irrelevant results. The semantic web, however, allows for more precise, context-aware queries. Next, the content. The traditional web is mainly designed for humans to read with limited context. In contrast, semantic web defines relationships between data, enabling also relationships with the context of this data. Lastly, on the traditional web, data is usually static and isolated. The semantic web, in contrast, connects data in a dynamic way, enabling information to be reused, linked, and integrated across different systems. The semantic web is built on a set of well-known metadata standards, approved by the W3C. Some of the main standards are RDF, OWL, and Sparkle, but there are many others. In this presentation, we'll give some basic ideas about RDF, OWL, and Sparkle. So let's start with the first one, the resource description framework, which is the basic data model for the semantic web. RDF usually structures its data by using a triple structure, namely a subject, predicate, and object. Each resource in RDF is identified by an uniform resource identifier, URI, that ensure that every resource on the web has a unique, let me say, address, making it easy to reference and link resources in a consistent way on the web. The other standard is the Ontology Web Language, OWL, which builds upon RDF to provide a more advanced vocabulary for creating ontology. Ontology that, as we can see later during the presentation, is a formal representation of knowledge within a specific domain. With this language, OWL, we can model more different and complex relationships, such as hierarchies, equivalence, disjointness, and much more. This standard also support reasoning task, namely enabling some smart agents to make the discovery of implicit knowledge. There are different versions and sub-languages of OWL. Each offers different level of expressiveness, which also correspond to different computational capabilities required. The next standard is Sparkle, which is the standard query language for working with RDF data. The main benefit of Sparkle is the fact that you can perform graph pattern matching to find parts of the RDF data that meet your specific query criteria. This allows to retrieve exactly the information we need. Okay, now let's take a look at some of the key challenges we can face when working with cultural heritage data. First of all, fragmentation. Museum, archives, and cultural organizations in general often store their data as separate silos, making it difficult to share and integrate information across different organizations. Then, each institution may use its own standards and metadata to describe their collections, and some data might be, for example, unstructured, which complicates linking or querying data across platforms. Finally, it's well known that the cultural heritage data often involves symbolic meanings, historical context, geographical connection. While these elements are essential for understanding the true meanings, the true significance of the data, they can be challenged to represent consistently across different data sets and across different platforms. In this context, Semantic Web offers powerful solutions to overcome these barriers and challenges. Firstly, it breaks down silos by linking data using uniform resource identifiers. Secondly, ontologies in this context can provide a structured, shared framework for representing data across different systems, making it possible the interoperability between different platforms. And finally, Semantic Web enables capturing complex relationships with the support of reasoning engines. So, in the last 20 years, Semantic Web technologies have transformed the cultural heritage data into connected network linked data. In this context, ontologies play a key role by providing the structure, namely the schema, that defines how data can be linked. And into last decades, much work has been done on developing specific ontologies and metadata schema for the cultural heritage domain. In this slide, we report some of the most important ones. CDOC CRM, of course, can be considered the most relevant one. Also, there's the functional requirements for bibliographic records, which is a standard used for cataloging and managing bibliographic records. There is also two metadata schema, FOAF and Dublin Core, which are not specific developed for the cultural heritage domain, but they are widely used in this domain. Then we have two Italian ontologies, the SAN ontology, which is an ontology able to describe the archival resources, and it has been developed by the Italian archivist system, and Cultura On, which describe the Italian heritage events. So we now move on to the second part of the presentation, where we'll first explore the theoretical foundation of the concept of ontology, and after that we'll focus more specifically on the ontology design and development process. So we already started exploring the concept of ontology, but now let's take a moment to define what an ontology actually is. An ontology, as we can see in this definition, is a formal, explicit specification of a shared conceptualization in a specific domain. Let's break down this definition into its main keywords for a clearer analysis. Formal means that ontology is based on well-defined logical principles that ensure clarity and consistency. Explicit means that it clearly specifies the knowledge of the domain by structuring it by means of concept, relationships, and constraints. And shared conceptualization means that we are referring to the abstract knowledge of a specific domain, and this abstract knowledge is agreed upon by a community, which is crucial for ensuring the interoperability across different systems. To understand the concept of ontology, we need to recognize its foundation in formal logic, and specifically into a family of formal knowledge representation languages called description logics. In description logics, a knowledge base typically organized into two main parts: the terminological box, namely T box, and the assertional box, the A box. The T box is a sort of schema in a database because it specifies the general knowledge from specific fact within a domain by the means of concept and role. For example, we could express using this statement with the L syntax that a painting is a type of artwork, and this painting is located in a museum. The A box, on the other hand, represent the real-world entities of the database. It corresponds to the data in a database settings, and we can state always using the DL syntax that, for example, the Guernica is an artwork and is located in the Museo Reina Sofia. Description logics brings several contribution benefits to the table. First, they provide a formal logical framework to represent the knowledge by means of concept, role, and individuals. And secondly, description logics allow automated reasoning tasks such as classification, substantiation, and consistency checking that are very useful to understand implicit knowledge and to detect that our knowledge base have no contradiction inside. The same structure used to represent knowledge in description logics is also found in the ontology web language, which are built around classes, properties, and individuals. So, as in description logics, classes describe general categories or types of things in a domain. For example, artwork, artists are classes. Properties, we have three different kinds of properties. Object properties are useful to link individuals to other individuals. For instance, by the mean as creator property, we can connect an artwork to its artist. With the data type properties, we can link individual to specific data values, for example, a birth date of an artist. And annotation properties are used mainly for documentation purposes. So they help humans to understand in what way they can use a class or a property, for example. Finally, we have individual, which are the real-world entities the ontology can represent. According to Guarino, which is one of the main experts in the field of the ontology, we can classify the four main category of ontology based on the level of generality and scope of the application. First, we have the upper ontology, also called top level ontology. They are most general and describe a broad concept. One example of upper ontology is scos or dolce. Then we have a domain ontology that focus on a specific area of knowledge, such as, for example, health or cultural heritage. They take some general concept from upper ontology and specify them to fit the particular vocabulary of the domain. CDOC CRM, for example, is a domain ontology. Then we have the task ontology that focuses on particular task or activity. For example, a task ontology might describe a process like diagnosis a disease or selling some products. This ontology specializes the concept from both upper ontology and from domain ontology. Finally, we have the application ontology that combine elements of both domain and task to describe concepts that are tailored to a particular specific application. So now let's move on to the next key aspect of this part, the ontology development process. Creating an ontology is not a one-time task because it's, as already said some previous presenters, an iterative process that requires continuous refinement and improvement. In the literature, you can find different design approaches for modeling an ontology. Okay, and in this slide, I reported three of these main methodology: the waterfall, the pattern-based, and the modular ontology modeling. The first one, waterfall, is represent a step-by-step methodology. You can find two different approaches, methodology, ontology 101. The second approach, pattern-based, such as extreme design, which is an example, uses predefined design patterns to guide the development process. Finally, the third approach, the modular ontology modeling, breaks the ontology into smaller, independent, manageable module. The choice of modeling approach depends on the specific needs of the application. It's important to keep in mind, okay, that there are always multiple solutions to model a domain, so there's no one right way to model a specific domain. Okay, now let's take a look at an example of a 6-step ontology development process, which is the output of a mix, the combination of two waterfall methods, Ontology 101 and meta-ontology. The phases of this process are as follows: specification, consider reuse, conceptualization, formalization, implementation, creating instances, and evaluation. So let's start with the first phase, the specification phase. This phase is all about defining the purpose and the scope of the ontology, as well as identifying the key requirements of the ontology. So during this phase, usually we ask a question like, what is the goal of the ontology? What is the problem that is trying to solve? Who is the responsible for using and maintaining the ontology over time? And how we can formulate competency questions to ensure that the ontology meets its goal and functions in a correct way. The second phase is very, very important because it's considered reusing some existing ontologies and metadata. These represent a best practice is on ontology engineering for ensuring interoperability and consistency. Basically, when we create a new ontology, it's really important to check whether some concepts has already been defined somewhere, and if so, we have to consider to reuse them. There are different benefits in reusing existing ontology. First of all, reduce the effort and the time required to create a new ontology from scratch. It helps to maintain, to ensure the consistency in terms of terminology. And finally, it makes it easier to integrate with other systems. When we talk about ontology reuse, there are different approaches we can take. If you want more details about this topic, you can refer to this publication by Carriero and other. One common approach is the direct reuse, also known as ontology merging. There are two ways to make this by means of the property all imports. If you want to include the entire ontology into your own, or you can use other properties such as RDFS is defined by, or RDFS also, when you want to reference to specific terms and concept from another ontology rather than importing the whole ontology. Another approach to reuse existing ontology is the indirect one, also known as ontology alignment or ontology matching. This is done by redefining the semantics of concepts using some axioms such as RDFS subclass of or our equivalent property. Over the years, ontology alignment has become a key research area, and many efforts have been made to automatize this process. As a result, different tools, systems have been developed, and each of them use different techniques for alignment, lexical indexing, semantic similarity. More recently, neural language models have been introduced to improve this process. For those interested in details about these tools and system, you can refer to this recent publication that talk about the last results of the ontology alignment evaluation initiative held last year in 2023. So, moving along the process, we now come to the conceptualization phase, in which we define the knowledge in terms of classes, properties, and constraints. or namely rules that restrict how data can be represented or related within the ontology. This phase is very, very relevant because it shapes the core structure of the ontology and its ability to represent the knowledge of the domain. The next phase is about formalization and implementation. Basically, in this phase, we translate the conceptual model into a formal model by using some formal languages such as OWL or RDF. So in this phase, we have to define the precise structure of classes, properties, and constraints. We have to formulate logical axioms, and we have to ensure the consistency, meaning we have to check there are no contradictions or errors in the model. There are several tools very useful to streamline the process of formalize and implement the ontology. The most popular one is, of course, Protégé, which is a graphical tool for creating and managing our ontologies, that offer also support in reasoning and in querying the data. There are also some Python libraries very useful, such as RDFlib and RReady2, that allow you to create ontology, manipulate data, making some queries, and much more. And when working with a very large data set and ontology, I suggest you to consider triple stores such as BlazeGraph and GraphDB that are essential to store RDF data and allow for efficient querying. So, moving on, we reach the creating instances phase. In this phase, we start to populate our ontology with actual data. Basically, we are bringing the abstract concept, define the ontology to life with the real-world example, making the ontology more concrete. The last phase is the evaluation phase, in which the goal is to assess, to ensure the overall quality of the ontology. For doing this, we can also we can take into account some evaluation criteria, such as the ones I report in these slides: accuracy, adaptability, completeness, consistency, and so on. Keep in mind that the ontology development phases that we have seen are not rigid or strictly sequential, since ontology is an iterative process, and it's common to revisit earlier phases and make some adjustments, refinements, and for example, after the formalization phase, we may go back to the conceptualization phase in order to redefine some classes and properties. Okay, covered the part related to the ontology development process. Let's move on to discuss about knowledge graph. Ontologies often serve as the foundational structure for a knowledge graph, in the sense that they provide the schema within a knowledge graph. It's important to note that there isn't a single common, universally accepted definition of knowledge graph. One common definition is the following: a knowledge graph is a graph structured knowledge base where nodes represent the concept and edge relationships. In the last year, knowledge graphs are increasingly being used in different domains, cultural heritage, finance, technologies, and much more, and are used as large words knowledge base. In these slides, I reported some knowledge graph example. We already explored also, during the past presentation, DBpedia and Wikidata, they are widely used also in the context of the cultural heritage. Another important knowledge graph in the domain is ARCO, which is built on CDOC CRM, and it's specifically designed to represent Italian cultural heritage data. The last two examples you can see in these slides refer to the Chinese cultural heritage domain. So I thought that given the framework of this seminar, it was important to mention them and include them into this presentation. The first one, the CICHM knowledge graph, is a multimodal knowledge graph, multimodal in the sense that it combines both text and images, focused on Chinese intangible heritage, and it contains 1.7 million triples. The last one is called the Women Multimodal Knowledge Graph and is based on an ontology named Chinese Painting and Calligraphy, which is built on CDOC CRM, that includes more than 1,000 artists and 12,000 works of Chinese painting and calligraphy. So, we are reached the third section of the talk. I would like to present two projects I'm currently working on with my colleague. And let's start with the first project that I would like to present. Is called Women Writing Around the Camera, which is an ongoing project funded by the Italian Ministry of University Research and the Next Generation Europe. The long-term goal of this project is to create a semantic portal that collects and organizes data around the autobiographies written by the Italian divas actresses such as Sofia Loren, Monica Vitti, Golerda Sapienza, and much more. It's well known that the autobiographies are much more than simple biographical records because they are complex narratives that link professional and personal experiences, emotions, reflections, feelings, and much more. Traditionally, these texts have been studying through traditional analysis methods, close reading and distant reading. As a part of this project, we developed a knowledge graph called WOW, which is the acronym of the project, to support the research and the study in this specific field. The WOW knowledge graph represents the backbone of the future semantic portal of the project. It's small right now because it currently includes around 40,000 individuals, but we are continuously updating to further enrich it. We published under the Creative Commons license both the data model using Payload, and the dataset is public, is available on Zenodo. The methodology used for building the WOW knowledge graph includes the following main phases. In the first phase, we collect all the data sources from autobiographies and also some external sources. Like DBpedia and Wikidata. In the second part, we focus on the design of the data model able to represent the requested data. In the third phase, we populate the data model with the actual facts. And then finally, we evaluate the fairness, the compliance of the data set. So the main source for the knowledge graph is the primary sources, namely the autobiographies of Italian actresses. We analyze more than 100 autobiographies written by 59 actresses. We extract a set of useful information, including nearly 500 segments of text that we call block quotation. We annotated this block quotation using 19 themes, namely there are concepts, and more than 200 keywords, and we annotated all the information included in this text, also the individual mentioned in the text. Our knowledge graph has been integrated with data from external platforms. And this data provides some additional context, including information about movies, co-actors, and other information about the personal networks of the actresses. Okay, in this slide, we represent the graphical representation of the data model along with the ontology that we used to integrate our data model. Classes are represented in gray color, data properties in gray color, data properties in green color, while object properties are represented by solid arrows. I don't want to go into the specific details of this data model, but it's important to highlight that the data model has been structured into main parts. The first part, highlighted in the red, focuses on the content of the autobiographies, which capture some bibliographic data, concept, keywords, and relevance block quotation. The second section, marked in blue color, provides broader contextual data linking actresses, writers to their personal, private, and filmographic network. Okay, this slide shows the process of populating the knowledge graph. First, the annotation were converted to RDF format, and we used this annotation to populate, to directly populate some relevant classes, such as these ones. We leveraged on name entity linking task with DBpedia in particular for the populating the person class, linking names to external data, and generating URIs for further querying. And additionally, we enriched the place and the film classes with other external data coming from DBpedia, but also Wikidata. Okay, looking ahead, we are about to release a new version of the knowledge graph with an additional of 12,000 of individuals, including new films and new persons. We are also extending the coverage of the text that we want to include in this knowledge graph. And finally, we are exploring the use of some large language models with a zero-shot learning approach to automatically annotate text with relevant themes and keywords without the need for dedicated training set. Okay, the second example I would like to present is about Sardinian traditional costumes, which are a rich part of the island's cultural heritage. This ontology, this project has been developed within the framework of a very large project named EINS. There are some exciting ontologies that partially covered the topic, but they didn't capture the specifics of Sardinian costume. And in order to address this problem, we developed the Bistiris ontology, which allow for detailed representation of costumes, focusing also on aspects like geographic and time to track the evolution of the costume. Just a fact, a small fact, Bistiris, the name of the ontology in Sardinian language, means to dress, to wear. Okay, we started developing the Bistiris ontology by collecting data from different sources, such as historical books, manuals, expert knowledge, and photo archives, which helped us to shape the knowledge into key concepts and relationships. In this slide, you can find some information about ontology, about its implementation language, about its matrix. We also applied some link and data principle to connect this ontology with other knowledge graphs, including ARCO. Okay, in this slide, we show how Bistiris models the characteristics of two traditional costumes, different from the same town named Azzara. One is for everyday wear, and the other one is for gala or bridal occasions. In this representation, the lilac ovals represent individual items in the ontology, while the blue boxes represent the class they belong to. While data properties are represented into these green boxes. This diagram helps us to understand how we can capture important details about these two costumes, such as the sources, such as the datation, the place, but also some important features, like, for example, the colors and the design of the of some specific elements. For example, in this case, the skirt. Okay, in this slide, we outline some of the key next steps for this work. First, we plan to expand the ontology to include also the description of traditional male costumes. We also planning to represent additional properties such as tailoring techniques and other technical characteristics of the costume. And lastly, we are exploring the use of convolutional neural networks to classify costume from images. This will help to automatically extract data and to support the growth, the population of the ontology. Okay, we reached the conclusion part. And for concluding, we are looking at some key challenges and new direction in this field. One big challenge is striking the right balance between making the data reusable and interoperable while ensuring its accuracy and its reliability. In terms of research direction, new research direction in the domain, of course, machine learning and large language models are offering new perspectives. Machine learning can help, for example, to automatize tasks such as classification, annotation, linking, while large language models bring added value by assisting in knowledge extraction, concept definition, constructing knowledge graph, and also in the query answering task. It should be very useful. In conclusion, combining both symbolic and sub-symbolic AI offers new opportunities and new perspectives for advancing research in the cultural heritage domain and the semantic web in general. So in this slide, you can find some references that I've seen during this presentation, and I would like to thank you for your attention.
Thank you, Laura. So if anybody has any questions, comments, curiosities. Maybe you can, yeah, thank you. Thank you very much.
Hi, thank you for the presentation. I had a small item concerning very specific aspects of your project about costumes. In the example you were giving about the ontological representation, you were pointing to data element about the datation, where the name was like late 19th century. I was wondering how you represent these vagueness and approximation in datation specifically, whether you've been using like that, I guess it's here called periodo with a capital O, which gathers some of these things, or whether you have a more precise way to characterize a late in the century or something like that.
Thank you for your question. If I understood well, because I have some echo, but you are asking what kind of schema we are using for datation, right? If I don't wrong.
Yes.
Sorry, Okay, the representation of timing is complex, as you know, and at the moment we are using the Wikidata timeline description properties in order to represent the timing of the costume. And at the moment we are representing some mid-century timing of the costume, but we would like to be more specific in datation, in the timing, the costume. So we are working on improving this part of the ontology.
Any other questions? Okay, then I'll go. I just wanted to ask, given your experience, what do you think about the latest emergence of large language models when it comes to ontology development? What are your thoughts in general?
Okay, I think that the knowledge representation field and sub-symbolic AI can cooperate together to make some improvements together, because large language models have some fascinating results during the last years, but I think that the knowledge representation offers more concrete representation of the reality, the knowledge. So I think that they should cooperate together in order to combine these points of strength. So I think that the large language models, neural networks can offer new perspectives, but it's important to work together to combine the two approaches.
Okay, thank you very much. If we don't have any other questions, we can proceed. Thank you, Laura. Thank you again.
Thank you.